Hey guys, today we are going to do some Lewis structures. I want to draw Lewis structures for these particles that I've shown up here. I'm using the word particles because I can't say molecules because one of them, this guy right here, is an ion. And I don't want to break the rules. I don't want to call it by the wrong name. So, in the spirit of proper pronouns or something like that, if you want to think of it that way, I'll just call them all particles. All right. So a Lewis structure involves an arrangement of particles showing the electrons that bond them together and the electrons that aren't involved in bonding. To get started for number one, I'm going to write the carbon at the center of this thing. The reason I'm going to write the carbon at the center is that it is surrounded by 4 valence electrons. If you look in your periodic table, you'll see that carbon, count across the row, it has 1, 2, 3, 4 valence electrons. And that means that it's a very common center when it comes to chemical bonding. So the carbon, that C looks weird. I don't like weird C's. There we go, that's a better C. This carbon is going to bond with the hydrogens that are around it and also with the chlorine. Now, you might say, how do you know ahead of time that the carbon is going to bond to the hydrogens and that the carbon is also going to bond to the chlorine? Why couldn't it be that the hydrogens bond to the carbon and also one of the hydrogens gets the special privilege of bonding to the chlorine as well? Here's why. It'll become clear when we actually go draw the picture. I'm going to draw hydrogen with its 1 valence electron, and this gets done 3 times, right? Because there are 3 of them. A shared pair of electrons between 2 atoms is exactly what a chemical bond is. There's 1 pair of shared electrons in between the carbon and this hydrogen. There's also one between the carbon and this hydrogen. And there's also one between the carbon and this hydrogen. So those shared pairs of electrons are all going to turn into chemical bonds. So I'll get rid of the electrons, and I'm going to write them as these lines, which signify that carbon is bonded to the 3 hydrogens. Now I've done the carbon, and I've done the 3 hydrogens. I need to put the chlorine in. Well, you can probably see where it's going to go. It's going to go on the right-hand side, where the carbon has an unpaired electron. An unpaired electron is a particle saying, please put something here, bond with me here. So I'm going to respond to that, and I'm going to give chlorine its number of valence electrons. Now, I've put the first one there already, but chlorine has, count across the row, 1, 2, 3, 4, 5, 6, 7 valence electrons. So in addition to that 1, I'm also going to put 6 more around it. Well, hold on. Look at what happened between the carbon and the hydrogens. Yes, you can probably see what's coming. We're going to be getting rid of that pair of electrons and replacing it with a chemical bond. At this point, I want to say, am I done with the Lewis structure? I've put the things there. Do they have what they need in order for this to be stable? The answer in this case is yes. All of the atoms in a Lewis structure should have 8 electrons around them, except there's one exception that applies a lot, and there's another one that applies only sometimes. Hydrogen, because it's so early in the periodic table, the very first element, is happy with filling up its energy level, which only needs 2 electrons. So that's why each one of these hydrogens is totally happy with just having that single pair of electrons that's next to it forming that chemical bond. So all of the hydrogens are happy. And the other particles here, the other atoms, I should say, the carbon and the chlorine obey the octet rule, which is that they're happy when they have 8 electrons. So let's count the electrons around the carbon. Remember that each one of those bonds contains 2 electrons, right? So there's 2 here, and 2 here, and 2 here, and 2 here. Well, 2 plus 2 plus 2 plus 2 is, of course, 8. And so carbon has 8 electrons around it. Notice how it doesn't end up mattering that carbon only brought 4 of those electrons to the party. It's okay that carbon only brought 4 because hydrogen supplies the rest. We could have asked the same question for the hydrogens. Why did they get 2 when they only brought 1 to the party? Well, forming chemical bonds is all about teamwork. So the pairs of chemical bonds, the pairs of electrons that form chemical bonds, get to be counted as electrons belonging to each of the atoms that form that chemical bond. Now let's look finally at the chlorine. It's not hard to see that you have 2 here, and then there are 2 also at this position, 2 also at this position, 2 also at this position. So chlorine has 2 plus 2 plus 2 plus 2 for a total of 8 electrons, and everybody's happy. All right, let's see how this applies to drawing the No2 minus. Let me see if I can get rid of those. Sometimes Zoom erases stuff that I don't mean to erase. Number 2. Now, quick pop quiz. What's the name of this ion? If you take a few seconds to look at the back of your sheet from your chem class, you'll be able to name this. It's one of the polyatomic ones. It is not nitrate. This is the nitrite ion. That doesn't come into building the Lewis structure for it, but it's good to be able to recognize these things anyway. I'm going to put the nitrogen in the center here. Why? Well, because there's 1 nitrogen and there are 2 oxygens. So it's likely that the nitrogen is going to be in the center and the oxygens are going to be hanging on at the edges. So I'll try drawing it that way at first. If it doesn't work out, I'll redo it. Nitrogen in the center. I'm going to put the dots around it just like I did with the carbon. Nitrogen has 5. Count across the periodic table. 1, 2, 3, 4, 5 is when you get to nitrogen. So 1, 2, 3, 4. And now I've got to pick a place to put the 5th one, wherever. You can put it top, left, bottom, right. It doesn't really matter. So now nitrogen has all 5 of its valence electrons drawn around it. I'm going to put the oxygens in a different color, just like before, so that I can keep track of what belongs to what. That first valence electron that I drew around that oxygen is a shared electron, which is going to make a bond between the oxygen and the nitrogen. 1, 2, 3, 4, 5, 6. That's the number of electrons that oxygen has around it as a valence. Its valence electrons, it has 6. Now, look ahead to what we'll probably be doing toward the end of this. That oxygen is, well, it doesn't have its full octet of electrons. It doesn't have 8 electrons around it. So we're going to need to find something to do about that, because right now this wouldn't be very stable. But we can replace that pair of electrons between the oxygen and the nitrogen with a bond, because, hey, that's what a pair of shared electrons is, right? A bond? Absolutely. So let's put the second oxygen in. We've put in the nitrogen, we've put in one of these. Now we just need to put in the other one. Oxygen has, remember we just did this, 6 valence electrons. So 1, 2, 3, 4, 5, 6. And I will get rid of that pair and replace it with a chemical bond. And so far, so good, except there's a couple of problems. The oxygens each are deficient. They each have 7 electrons instead of 8. Now, sometimes molecules can be happy with this. They can be a little bit unstable, but I'm going to call 2 things to your attention. First of all, if you have an unpaired electron on 2 atoms that are already bonded together, and they each need just 1 more electron, what's probably going to happen is that those electrons are going to actually zoom around to be in between them and form what's called a double bond. So what's going to happen is that these electrons that I've circled right here, I'm going to get rid of them. And they are going to form another bond between the oxygen and the nitrogen. So now look at what happens to the oxygen. As a result of this, it gets to share 1 more electron with the nitrogen. And it has 2, 4 electrons in that bond. Check it out. It's a double bond, right? 2 electrons per bond, and that's a double bond. 2 times 2 is 4. There's also 2 up here and 2 over here. So the oxygen has 8. it has its octet full. That's good. That's what we want. What about the nitrogen? The nitrogen also has this 4. It has 2 here and 2 here. That is also 8. So nitrogen is very good. It's happy. It's nice. The oxygen on the right, though, it's not doing so hot. But here's where we get to use the fact that this is an ion. We haven't mentioned this until now, but this means something. This means that you have an extra electron. If you have an extra electron, you can put it wherever makes sense in order to increase stability of the ion. Guess where it's going to go? Oh yeah, it's going to go in that empty spot right next to the oxygen. So right there, this is an extra electron. Don't worry, I'll take that label away in a second. But just to be clear, that right there is not ordinarily around an oxygen. It's there because we can make this an ion by putting in one more electron. Okay, so now that I've done that, the nitrogen is still happy because it didn't get any more or fewer electrons around it. The oxygen on the left-hand side, that is happy still because nothing changed with that. The oxygen on the right-hand side, that's good too now because it has the 2 from the bond and it has 2 here, 2 here, and 2 here. That means it has a total of 8. Well, guess what? Now this is all stable. So what you usually do when you write a Lewis structure for an ion is you put the whole thing in a big set of brackets, and then you write the charge on the outside. The reason you do this is so that it doesn't create the impression that that charge lives on just one of those atoms. Like if I didn't do that, if I put the charge right there, then it makes it seem like right there. Yeah, it took a second to show up. If I put the charge right there, it creates the impression that that minus sign, the negative charge, belongs to the rightmost oxygen atom. Well, that's not actually true. What's really true is that the charge belongs to the entire ion. And so a common practice is to put a big set of brackets around it and write the charge on the outside of the brackets. Let's do the last one, and then I promise we're going to be done. I know, sometimes I get sick of my own voice too. Nah, let's see if I can erase exactly what I want to erase. Good. Okay. This one is different again. These are all supposed to be covering, slightly different ways of doing it. Because here we don't have a well-defined single center. When you have what's called a multi-centered molecule, the best way to approach it is usually it's going to be made out of a bunch of carbon atoms strung together. So build a backbone from carbon and then branch off. So if you build a backbone out of the carbon atoms that are in this molecule, you're going to be able to make the other stuff come off the top and off the sides. Watch this. I'm going to put the 2 carbons that are there. There's one right here and another one right here. I'm going to put them both in a row, and I'm already going to draw a chemical bond between them. Carbon is going to be bonded to carbon. So if I call this like carbon number 1, that's carbon number 1. And if I call this carbon number 2, that's carbon number 2. But it doesn't really matter which one is which. The first carbon has 3 hydrogens bonded to it. So this is going to be the easiest part of this problem. I'm going to just draw the hydrogens already with their bonds in place. And the first carbon, the one on the left-hand side, that's already happy because it has 4 bonds surrounding it, which is an octet. Okay, so that guy is fine now. Let's talk about the other carbon. Now, at first, this seems like it's not going to be possible because we've got like an H coming off here and an H coming off here, and then the OH being written in the last part of the chemical formula makes it seem like, you know, like I'm supposed to somehow write an O and then an H over here, but that's not possible because a hydrogen can't form more than one bond. So that can't be what happens. And also, this would leave the carbon unhappy because it doesn't get to form all of the bonds that it wants. But this actually provides the solution, because what I can do is, instead of writing the hydrogen and then trying to branch off that, what I'm going to do is write a hydrogen right here. Sorry, I'm getting a bit mixed up with the colors. I know I started out with the bonds being in red, but now I'm going too fast for that. The carbon will be bonded to the hydrogen over there. And so far, I've got the 2 hydrogens bonded to the carbon. So far, so good. What I'm going to do is branch off the carbon with the oxygen. The reason this is good is that now it gives the other hydrogen somewhere to go that makes sense. So that carbon has its 4 bonds and it's all set. Up until now, it wasn't really necessary for me to put in valence electrons because everything has just been bonds. But now that I'm getting kind of close to the end, I'll start putting in valence electrons in just a sec. The oxygen has to be bonded to a hydrogen as well. Now I'll start putting in valence electrons. Oxygen has 6 valence electrons. Again, count across the table, 1, 2, 3, 4, 5, 6. That's where you hit oxygen. It has brought one of those to this bond, and it's brought one of those to this bond. That means that there are 4 remaining to be drawn. So I'm going to put 2 right here and 2 right here. Is oxygen happy? Think about it. It's got 2 valence electrons, I'm sorry, 2 electrons in that bond. It's got 2 in that bond. It's got 2 in that bond, and it's got 2 in that bond. Happy? Yes, because it's surrounded by 8 electrons. That's exactly what you want. So this is a fully correct Lewis structure for this. Well, I won't make you name this. It's ethanol, but you know, that's a story for a different time. Hey, listen, if you found this helpful and you'd like some help with your assignments, feel free to set up an appointment with me. You can always get in touch with me by giving me a call or a text at 617-966-3198. You can also visit my website at sntutoring.com. I'd be happy to help you either in person here in Needham or online on Zoom. Have a great day.